Hello guys, this is the next video, Building Docker Images. In the last video, we looked at Docker architecture. In this video, we're going to take a look at an example of building an image. We built an image using the commit command of Docker. Although it works, I can see a big problem with it. It is not repeatable. There is no easy way of rebuilding the image once and over again when the software installed in the image is patched due to new vulnerabilities or versions. In order to solve this problem, Docker provides a better way of building images with Docker files. A Docker file is a file that contains a set of ordered commands required to leave the image ready to be used. Things such as installing software or upgrading the version of the kernel, as well as adding users, are common activities that can be carried in a Docker file. Let's look at an example. We are creating our image based on the latest Node.js image. A new folder is created in /app. Our application will be installed here. The working directory is set to this new folder. Then we have a copy package.json and install the Node.js dependencies. Remember that we have already set up the working directory to /app, so the run command will be run in the /app folder. Then copy the rest of the source code. Next is expose port 8080 to the outer world. Finally, run npm start. It is very simple once you have done it a few times. One thing to keep in mind that might drive beginners crazy is cmd versus run. In this Docker file, sometimes we use run and sometimes we use cmd, but both of them seem to do the same thing, that is, run a command. There is one difference. The run command will run the command when building the image. The cmd will run the command when the container based on the generated image starts. Also, run creates a new layer, whereas cmd uses the writable layer of the container. Now, it's time to test the Docker file. Before building the image, we need to build a small Node.js application that is going to be used as the software running in the image. Let's create a new folder with 3 files. Now, we will create the first file. Here's the content of package.json. Next, we will create the second file. Here is the content of index.js. Now, we will use the same Docker file as before. And now, with these files and the Docker file described before in the same folder, we will run the docker build command. After a few seconds, our image would be ready for use. Let's check it. Now, we list our images with the docker images command. We will see an image called My Node App. Now, we create a container based on the image using docker run command. We will get the output like this. In this video, we have built Docker images. In the next video, we will see Docker registries and volumes. Hi guys, welcome to the next section, Docker. In this section, we will see Docker architecture and internals. We will then see building Docker images. After that, we will look at Docker registries and volumes. Finally, we will see Docker networking and compose. Now, we move on to the first video of this section that deals with Docker architecture. In this video, we're going to take a look at the architecture and concepts of Docker. We will also see Docker internals. Next, we will see Docker's client. One of my preferred ways of learning is through experimentation. In order to explain the Docker architecture, we're going to show an example, but first, we need to install Docker itself. In my case, I'm working with Ubuntu. At this link, you can find the distribution that suits your needs with a very clear set of instructions. Once you've installed Docker, run this command. We will get a message from Docker. This message shows that your installation appears to be working correctly. Let's see some newly introduced concepts. First one is Docker Hub. This is a central repository which is public and private, where users can push images that they build locally. A Docker registry is used to carry the images across different stages of the deployment pipeline. The next concept is Layer. Docker images are composed of layers. A layer is basically an ordered file system difference. A Docker image is a stack of these layers leading into the final image. When you change a file in an existing image, a new layer is created, but the rest of the layers of the images are reused so we can save a lot of space. Next are the Docker daemons. Docker follows a client-server architecture. The Docker daemon is the server part that could be operated via a representational state transfer API. Last one is the Docker client. Docker client is a command-line interface, CLI, used to operate a Docker daemon. It might be a local daemon or a remote one. The last three concepts are the key for drafting the architecture of Docker. Let's take a look at the figure. The client-server architecture predominates the software. In this diagram, we can see how the Docker CLI is able to manage a local instance of the Docker daemon, but is also able to talk to a remote daemon by setting an environment variable called Docker host. One of the key points of Docker is that it completely leverages the virtualization to the Linux kernel, making it impossible to run Docker on Windows or even Mac, as it uses the capabilities of the Linux kernel. The solution to this is to create a virtual machine with Linux that runs the Docker daemon, and the CLI will talk to the virtual machine to run Docker commands. Now we move to Docker internals. Docker provides you with only a runtime for your applications. You can limit the number of cores and the amount of memory to be used by the container. By the end of the day, the kernel running your container is going to be the same as the kernel running your host machine. The proof of that is in the way Docker organizes images. It calculates files system differences and packs them in layers that can be reused. Let's pull a fairly big image. As you can see, Docker has pulled 5 layers, which basically tells us that the Ubuntu image was built in 5 steps. Now we're going to run an instance of Ubuntu. In Docker, an instance of an image is what we call a container, and the main difference between an image and a container is the top writable layer. Layers in Docker are stacked in the read-only mode to compose the image, such as the diffs in several patch files. Let's demonstrate this. This command runs /bin/bash in an instance of the Ubuntu image. The I and T flags allow you to use the container as if it were a virtual machine allocating a virtual TTY, T flag, and creating the interactive session that is the I flag. Now we can see how our prompt has changed to something like this. It does not necessarily have to be the same, but it should be similar. Note that your prompt is now a root prompt, but don't get too excited. It is just inside the container. We will create a file to alter the file system using the touch command. Now we can disconnect from the container with the exit command. As you can see, the prompt is back to your system prompt. If we run the docker ps command, we can see that there are no running containers. But if we run docker ps-a, we'll show all the containers, not just the running ones. This is a container that has been created from an image but is not running anymore. As we said earlier, the only difference between this container and the image is the top writable layer. In order to prove this, we're going to create a new image out of the container that we ran a few minutes ago. In our case, I'm using this reference because it is the one shown in the output of docker ps-a command. In fairness, you don't need to type it all, just a few characters will do the job. If everything went well, the command should output an SHA-256 checksum and return the control to you. Now run Docker images to list the images in your Docker. The output should be similar to this. As you can see, there is a new image called My Ubuntu that we just created. Now we want to check the difference between the Ubuntu image and the My Ubuntu image. In order to do that, we need to inspect the layers for each image and see the difference. The command we're going to use to accomplish this task is docker history, with the name of the image as the third parameter. First for the Ubuntu image, then for my Ubuntu image. Quite illuminating. The image My Ubuntu is the same image as Ubuntu except for the top writable layer that we just created by logging into the machine and creating a file. This is very smart because even though both of the two images use around 130 megabytes of space, the only extra space used for the second image is the top layer that, in our case, uses only 20 bytes, leading to a usage of 130 megabytes and 20 bytes for the two images. A container is the exact same thing as an image, but with a different top writable layer, so running an instance of the container uses only 20 bytes of space. As you can see, the engineers that created Docker thought about everything. The way in which how Docker stores the images in the hard drive is the responsibility of the storage driver. Docker can make use of different drivers and store the images in different ways. The default driver stores the images on the hard drive, creating one file per layer with the checksum of the layer as the name of the file. Now, let's see Docker Client. If you have dug into Docker a bit before, you can see that the commands are quite verbose and not as intuitive as you might think. The most common use case is using this combination. This command basically does one simple thing. It runs a container in the interactive mode and allocates sudo tty. This allows us to interact with the container executing the commands. Let's see what that means. The command should return a prompt similar to this one. What just happened? The prompt changed to root with a strange number in the host section. We are in the container. Basically, now we can run commands that are going to be run within the container. To exit the container, just type exit and the control should be returned in the terminal to your host machine, leaving the container running in the background. Imagine that you spin up a Jenkins server and you don't want to have your terminal attached to it. In order to do that, we just need to add the -d option and drop -i and -t. Once the image is pulled and it starts running, the control is returned to terminal. The last line in the output, and it should be a long string of characters. This is the hash of the running container. If we execute docker ps, this output will be produced. Note that the value under container ID matches the first few digits of the hash. Now in theory, we have a running instance of Jenkins that. As you can see, it is listening on port 8080 and port 50,000. Let's try to browse localhost 8080 with an internet browser. Nothing. Basically, our browser cannot open that URL. This is because we haven't told to Docker to bind the container ports to the local ports of the host machine. In order to do that, we need to first stop container and then start it again with a special parameter. It's time to learn how to stop containers. We have two options here. The first option is stop the container. With the stop option, we send sig term to the main process within the container and wait for it to finish. Then we send sig kill. The second option is kill the container. With the kill option, we send sig kill to the main process in the container, which forces an immediate exit without being able to save the state. In this case, which one you choose is irrelevant, but please be careful. When you're running in a production environment, make sure it's fine to kill a container. Before doing that, as with the stop option, we're giving the running software the option to save the current transactions and exit gracefully. In our case, I'm going to kill the container using docker kill command. Docker is smart. I did not need to specify the full container identifier. With only a few characters, Docker is able to identify the container and kill it. When we killed a container previously, we have a layer left that leads into a dead container that we can explore by adding the -a option to the docker ps command. In this example, we're going to remove the layer using docker rm command. That's it. The container never existed in our host. Now, going back to the Jenkins example, we want to run Jenkins in a way that we can access the running instance from our browser. Let's modify our command and run it. After a few seconds, if we go to localhost 8080 in a browser, we should see the initial configuration for Jenkins. It will ask you for the initial password to be able to proceed. Let's explain the command first. We can see a new option here, that is -p. As you can guess, -p comes from the port. In fairness, you could change -p for --port, and everything will work as expected. With the -p option, we map ports from the host, your machine, to the container. In this case, we're mapping port 8081 from the host to port 8080, and port 50001 of the host port to 50,000 of the container. But how can we map a different port in the host? Well, it's fairly simple. After running this command, we have two instances of Jenkins running. The first one is exposed in port 8080 of your machine. The second one is exposed in port 8081 of your machine. Note that even though we don't use port 50,000, I've changed it to 50,001. As our machine's port 50,000 is already busy with the first instance of Jenkins that we ran earlier on. As you can see, Jenkins is asking for a password, and the initial web page in localhost 8080 states that this password is in the logs or in the file system. Focusing on the logs with Docker, we can fetch the logs for any container registered by the daemon at any time. Let's try it using the docker logs command. In my case, the running instance of Jenkins on port 8080 has an ID that starts with 76561. Another interesting and common option in Docker is passing environment variables to an application running inside the container. If you think about it, there are only three ways in which we can configure an application within a Docker container. The first way is environment variables. The second way is volume with data. And the last way is fetching the configuration from the network. Let's take a look at the official MySQL image from the Docker Hub at this link. MySQL is a popular database server that has also been Dockerized. If you read a bit through the documentation, one of the config options is the root password for the MySQL database. In fairness, the Quick Start example points to the right direction. The new option here is -e. This option allows you to pass an environment variable to the container with the value that you want to specify after equals to. Next, we're going to run the docker inspect command. In this case, the ID is that results from running MySQL on my machine. There should be a huge JSON output in the terminal, but one section in particular, config, has a subsection called env. There it is. The environment variable that we passed, MySQL root password, is now accessible from within the container as the environment variable. In the docker inspect command, there is a lot of very valuable information. The best way to check what is going on is through the documentation on this website. There is also a reference of the commands of your current Docker installation available under the Docker help command. In this video, we've looked at Docker architecture. In the next video, we will see building Docker images. Hi guys, this is the last video, Docker Compose. In the last video, we looked at Docker networking. In this video, we're going to take a look at Docker Compose working. The majority of the time, Docker is synonymous to microservices. There is no technical limitation to running a monolithic app on Docker, but when the orchestration software comes into place, it really defeats the purpose of containerization. When dealing with microservices, it is very common to have several services running at the same time when developing. The new services will lean on the existing ones to execute operations. In order to achieve this setup, Docker facilitates a tool called Docker Compose that by creating a YAML file with the definition of our containers. It can spawn a full ecosystem of containers. Docker Compose used to be very popular in the beginning of Docker. Let's look at how Docker Compose works. This is YAML file. It is a Docker Compose definition. As you can guess, there are two components: a web application, the current folder, and a database, Postgres. Now we will save the file to a folder with the name dockercompose.yaml. This is a typical case of an application connecting to a database. In order to simplify this, our application is just going to be a dummy application with this code. We save this file as index.js. Now we will create a package.json file. And our Docker file is very simple. This Docker file will install the required dependencies and run npm start in the root of our app folder. As you can see, the application is very simple, and it only tries to resolve the name DB instead of connecting to the database. We're going to demonstrate how Docker Compose wires up the containers. By now, there should be 4 files in the work folder. Let's see it. Going back to our Docker Compose file, we can see that in the My App definition, we asked to build the current folder. We specify that the container itself is dependent on another container called DB. This means Docker take action and connect the two containers, being able to reach DB from My App by name. In order to achieve this, there's an entry created in etc hosts with the IP of DB, so My App will be able to resolve it. After proper indentation, our file will look like this. Now we will run the Docker Compose up command. Once it finishes, there should be quite a long output, but there are some lines that indicate our success. The highlighted section tells us that My App is able to reach DB by IP as they are on the same bridge network. Let's see what happened here. Docker built the image for the current folder from the Docker file. Docker pulled the Postgres image from the Docker Hub. Docker started the images in order, first DB and second My App, as specified in the dependencies. In this video, we've looked at Docker Compose. This section started with Docker architecture. Next, we built Docker images. After that, we looked at Docker registries and volumes. We then saw Docker networking and Docker Compose. In the next section, we will see continuous integration. Hi guys, this is the next video, Docker networking. In the last video, we looked at Docker registries and volumes. In this video, we're going to take a look at networking and user-defined networks. Networking is an important part of Docker. By default, Docker comes with 3 networks that we can inspect by executing the docker network ls command. It should produce output similar to this. Let's explain the different networks. The first network is Bridge. This is the default network. It is an entirely different stack from the host machine, with a different IP range in the bridge mode. The containers created without specifying the network are attached to the default bridge network. The next network is Host. In this network, containers share the network stack with the Docker host. If you inspect the configuration in the container, you will find that it is exactly the same as in the Docker host. The last one is None. This is easy to guess. The container gets attached to no network, just the loopback interface in the container. Now it is time to look at some examples. We're going to use BusyBox, which is the Swiss Army knife of the Docker images. It has several Unix tools that we could benefit from, but in this case, the characteristic that is going to benefit us is the fact that it is a functional Linux on a reduced space. Let's run this command. As you can see, we gain root access to a running container. The next step is to execute if config inside the container. It should give us two interfaces, ETH0 and LO. The IP might change, but you should see these two interfaces. Comparing the IP with the IP in your Docker host, we can validate the fact that the container is running in the bridge network, as the IP and network are completely different. Now, let's spawn another container with BusyBox in a different terminal. By now, we should have two BusyBox instances running. They should have consecutive IPs. In my case, the IPs are 172.17.0.6 and 172.17.0.7. If we go back to the terminal of the first instance of BusyBox, we can ping the second container by IP. This is because they both belong the same network, which is the default bridge one. In order to run the containers in the host network, we just need to pass --network equals to host flag to the Docker run command. Our container is sharing the network stack with the Docker host. But be careful if you're on Mac or Windows. The Docker host is a virtual machine, so don't attempt to access it through localhost. You will need to find the IP of the virtual machine running Docker. Let us use the user-defined networks. It is also possible to create custom and isolated networks in Docker. This is interesting from the security point of view, as it enables us to segregate different containers on the network level, so we can enforce a higher level of access control. In order to create a network, we just need to execute the docker network create command. And that's it. Well, that is a simplistic approach, but it works as expected. As you know, networking is a complicated subject, so Docker provides options to customize ranges, masks, and other parameters. The user-defined networks are of the type bridge. Once the network is created, you can run new containers in that network using this command on a new terminal. As expected, these containers will be isolated from the other networks. In this case, the two containers are launched in the bridge network. In my case, the third container, the one just launched, has the IP 172.18.0.2, whereas the two launched in the bridge network are 172.17.0.6 and 172.17.0.7. Issuing a ping command between containers in different networks results in 100% packet loss. In this video, we've looked at Docker networking. In the next video, we will see Docker Compose. Hi guys, this is the next video, Docker Registries and Volumes. In the last video, we looked at building Docker images. In this video, we're going to take a look at different types of registry. We will also see Docker volumes. Docker is interesting for running applications, but it is also a very interesting choice to create command line tools that other developers can benefit from. In order to distribute images, we have to rely on exporting or importing the image or using a registry. A registry is basically a software that allows us to store and distribute Docker images. There are two types of registries, namely public registries and private registries. Let's take a look at the different registry types. First, we have the public registries. The most known of the public registries is Docker Hub. It is the official and default registry that every Docker installation knows of. Also, it offers private repositories, but the most interesting feature is the fact that all the official images are available on Docker Hub. Let's see how we can use it. First, you need to create an account. Once we are registered, we will create a new repository. This repository hosts an image called Modern DevOps. We're going to push one image into it. Here, we will enter all the required fields. Once it is created, you can see that Docker Hub suggests that you pull the image with this highlighted command. In your case, packed will need to be replaced with your username. Obviously, we're not going to pull an image that is not there yet, so let's push an image. Previously, we had created an image called My Node App. we're going to use this image to test Docker Hub. Docker relies on a tag system to know where to push the image or where to pull from. As we are working with the default registry, we don't need to specify the URL, but we need to specify the user and the repository name. Let's run this command. And then we will run the docker push command. After a few seconds, our image is available on Docker Hub. As we marked it as public, everybody can pull and use our image. Now we move to private registries. But what happens if we want to store our images in our private registry within our infrastructure? Well, we have some options. If we're using cloud providers such as Google Cloud Platform or Amazon Web Services, they provide a Docker registry that is only accessible from within your account, and you can specify the region in which your images live. In AWS, the container registry is called EC2 Container Registry, and in GCP, it is called a Container Registry. If your infrastructure is one of these private clouds, I encourage you to use it as you can leverage the access to the access controls provided by the platforms. Sometimes we might find ourselves in a situation where we cannot use a cloud provider as our system has to be built on premises. This is when we need to use a private on-premises Docker registry. From all the range of registries, there are three that I find particularly interesting. The first one is
Quay.
This is a complete registry in the current market. It has some interesting features, but the one that is probably the most interesting is the ability to scan the images searching for security vulnerabilities in the installed software. The next one is Registry. This is the plain name for a plain concept. It is the official implementation of the Registry API and comes packed in a container. It has no interface or access controls by default, but it does the job. It also provides the storage management drivers so we can deploy our images to S3 or Google Cloud Storage buckets, as well as many other options. Registry is free and can be pulled from Docker Hub. The last one is Docker Trusted Registry. This is part of the enterprise version of Docker. Like pretty much any other commercial registry, it provides static container analysis as well as storage management drivers. Docker Trusted Registry is not free, so a license has to be paid for in order to use it. Now, let's move to Docker Volumes. An important part of any application is the storage. In general, Docker applications should be stateless, but with the new orchestration software, more engineers are moving toward containerized databases. Docker solves this problem in a very elegant way. You can mount a folder from the local machine into the container as if it were a normal folder. This is a very powerful abstraction as it leverages the ability to push data out of the container to be saved into a network-attached storage or any other storage technology. Let's start with the basics. We will just run a MySQL database. This works. It actually does what is expected. It launches a container with a MySQL instance in it. The problem is that all the data is going to be written to var lib MySQL, and this folder is mapped to the top writable layer of the container. The only way to save data is actually committing the changes and creating a new image that is not manageable, and of course this is not the only way you want to do it. Think about it. If you remove a file in Docker, you are doing it in the top layer, which is the only one writable. So in reality, you're not removing the file, you're just hiding it. The file is in one of the layers using the space, but it is not visible. Docker records differences, and a layer itself is a set of differences from previous stacked layers. Instead of committing the changes into a new image, we're going to mount a folder from our Docker host into the container. Let's alter the Docker run command a bit. Now we have a new flag, -v, followed by the data value. The meaning of the command is very simple. Mount this folder into this path of my container. As you can guess, the data folder, in my case, it should be present in your current directory. So if it wasn't present, create it or modify the path to suit your setup and launch the container. This use case can only be achieved through the -v flag. Mount a selected folder from the host into the container. Now we execute ls inside the data folder. As you can see how MySQL has actually written data files corresponding to the databases created in Bootstrap. Docker volumes are not limited to one per container, so you can replicate the -v flag as many times as you need in order to match your requirements. Another way of mounting a shared folder between the container and the host is just specifying the path inside the container. For that, we run this command. This command will mount a folder from our Docker host into the container. The folder in the Docker host will be managed by the storage driver and Docker itself. Let's run the docker inspect command. The output is familiar, but now we're looking for different information. We are actually looking for a section called mounts, which looks like this. This is also possible through the volume instruction in a Docker file. The JSON is telling us which local folder is going to be mounted in the container and provides an interesting insight. The volume has been named by Docker. This means that Docker tracks the volumes that are mounted in any container and can be listed through an API call. Let's run the docker volume ls command. This output should be produced. We can also create volumes through an API call using the docker volume create command. This volume is created in the same way as the previous example. It is up to Docker to decide which folder on the local machine is going to be mounted in the specified path in the container. But in this case, first we are creating the volume and then mounting it to a container. You can even inspect the volume using docker volume inspect command. It will give us this output. Now we use this named resource and mount it into our containers, just referencing the name. The last interesting use case in volumes helps us share the configuration across different containers. Just imagine that you have a fairly complex setup that leads to a gigantic Docker command with several -v. Docker provides us with a much simpler way of sharing volume configuration across containers using this command. This is very simple and intuitive. MySQL 5 will spawn with the volume configuration of MySQL 4. In this video, we've looked at Docker registries and volumes. In the next video, we will see Docker networking.